taking what we know about how to measure things, how to write numbers, we had to take baby steps. Okay? How to measure things, how to write numbers, how to do calculations, how to convert things. You can never forget that. It's never going to go away for the rest of the semester. Okay? So know that. This last chapter we talked about what matter is, what energy is, how they are related, a little bit about heat energy, physical, chemical properties, that kind of stuff. So far, digestible material. Okay? Hopefully all of it will be, but certainly I hope that at this point, other than just maybe some basic math steps anyway, some of you may be still stuck on a little bit of that, but as far as not having any idea what I'm saying at any given time, I hope we're not at that point yet. Okay? Hopefully at least you can understand what the words that are coming out of my mouth to some degree. Okay. Now, this chapter, we're going to focus on the actual atoms and the elements that are involved in this matter. We're going to look at different kinds, different types, and we're going to take a periodic table, completely dissect it, and do more with the periodic table than you've ever done in your entire life. So what you're going to need to do, especially for next lecture, if you don't have it now, is get a periodic table that you can make notes on. Okay? So print it. I have one on my webpage you can print off, or you can find any. There's a billion of them on the internet. Pick which one you want. If you want one with fancy unicorns and rainbows, I'm sure you can find one. I don't care as long as it's accurate and real, because you will need to make some notes on this to help you. All right. Something here, just to keep it pace with blowing your mind kind of thing. I don't know if you grasp just how small I'm talking when I talk about atoms. To give you an idea, say you had a pile of pea gravel, a bunch of little tiny stones. If I took one of those stones, okay, one of those little pebbles, and I looked at all the atoms that were in one of those tiny little pebbles. Now, if each of those little atoms, as many of them that we have in one tiny pebble, if I could take all of the atoms that were in that pebble and make them as big as, each atom as big as the pebble itself. Does that make sense? You follow me? If I make all those atoms as big as the pebble itself, you would have a pile of atoms, for example, bigger than Mount Everest. Okay? That's how many atoms are going to be involved with what we're dealing with. So it's going to be impossible to count all the atoms that are in the universe. No one would ever attempt that. Okay? There's a bunch. What we can do is learn how to deal with very large numbers mathematically. We'll get to that in upcoming chapters. And what we can also do is appreciate how small these are, yet how powerful they are, because they drive the existence of all matter. These fundamental tiny little things that we call atoms that can't be stripped down any further into a functional unit. That's it. That's as far as we go to create, well, in this class, to create matter. Until we get to advanced physics and you talk about the different forms of matter, dark matter, antimatter, all that kind of stuff. That's way out there. All right. So that being said, I'll let you read this yourself. I don't need to say that. It would make sense that sodium, for example, a lump of sodium behaves a certain way because of all of the atoms that comprise it. So the behavior that we are going to witness is due to the individual atoms themselves that make up this sample. Okay, so we probably know this based upon that famous chapter 2 in all science books. You at least learned what an atom was, what comprised the nucleus, what was going on around it, that kind of thing, right? We know atoms are composed of three main pieces that we're going to discuss here. There's more that we're not going to discuss. Protons, neutrons, and electrons. There are quarks that make up quarks that make up protons. Tend to be about three different small pieces of things called quarks that can arrange themselves to make the different kinds of protons that exist, but that's beyond what we're going to talk about here. Okay? We've got protons, neutrons, and electrons. Basically, the only thing we can do now to get more, when I said more, is to take a neutron or a proton and dissect it. Are there any pieces of a proton or neutron? But we're not going to go there. So protons, neutrons, and electrons. the neutrons and the protons make up the nucleus, okay? And the electrons are buzzing around the outside. Now, it's incredibly, incredibly complex in terms of how those electrons are buzzing around the outside. They're not just buzzing around out there randomly in this little orbit like little planets, as you will see. And when we get into quantum mechanics, it's much more complicated and it's fascinating. It's absolutely unbelievable. They disappear. Where do they go? Do they go into another dimension? I don't know. What is reality? Is this real? Does matter exist and then not exist for fractions of a second? In which case, how do you account for that? Based upon the conservations that we've talked about. Okay. Head explode. One thing that I'll keep in mind as we talk about this atom to get an idea, I like to tell my students sort of how to imagine an atom. You realize that you're a mostly empty space. Okay? The reason that you are mostly empty space, and hopefully this will become clear as we go on, is I know you don't buy it. You think, if I'm empty space, why can I do this? It's because the amount of space that makes you empty is very, very small. And you're not, if you had some kind of probe that would fit into this area right here, you would poke right through yourself. But the problem is, what you're using to poke is a big conglomeration of atoms coming up next to other ones, and you're not going to be able to fit through any holes that you have. Okay? Think of it like, in keeping in with the spirits of the weekend, you're at the RCA Dome, okay, watching the Colts play. About time. You're at the RCA Dome watching the Colts play, and you take a golf ball. You put a golf ball on the 50-yard line, right in the middle, the center of the field, on the 50-yard line. You look up, everything around you, you see all the seats, you see the edge of the building, and all of that. That would be the size of the atom versus the size of the nucleus that's actually in that atom. Okay? There's a whole lot of space there. The actual protons and neutrons, which comprise, by the way, all of the mass of that atom, is all concentrated into those protons and neutrons. All that space that you see out and around the edges of that stadium and everything in between is all the room in which the electrons have to roam. They can run around all in that space. And they're virtually massless. They're almost right at that edge where they're just energy, but they're not. They have a calculated mass, but it's extremely, extremely small and considered negligible, to the point where it's not even figured in a lot of times into calculations. So you've got all this space. Now this makes sense, and you have to agree, otherwise you don't believe that X-rays are real and that they're just alien pictures or something that someone sent to you. To take an X-ray, you've got to count on the fact that there is radiation that has the ability to be small enough to pass through areas like this. And when it can pass through areas, things that have more density, for example, like your bones, atoms are closer together because that stuff's more dense. That means there's more likely to be a reflection of the energy as it's bombarded towards you to be reflected back. That's what creates the picture that you see. Some of that softer tissue, you can still see remnants of it on there, but there's a lot more space in those atoms on the softer tissue. That stuff goes right through there. It goes through these spaces, so you have to believe, there's no reason that you really shouldn't, that we are mostly empty space. UV radiation coming down from the sun. You get a sunburn and that kind of stuff. I mean, a lot of that stuff goes right through your skin. It doesn't go deep. UV radiation is not energetic enough to penetrate and go through your body. It goes a little ways down into your skin on the top layers, and then it sort of just gets absorbed by everything that's there. Other things, though, like gamma rays that would come from a nuclear explosion. Another awesome show on TV, Jericho. I'm pumped. I can't wait till it comes back on. I've been trying to get online and read all the stuff, It's awesome. It's freaking me out, though, because that's not fair. Because they're making an online component of the show. And you got to go there for hints, and you can learn about it, and then you got to watch TV. That's too much, man. I just want to watch the TV show. I don't have to make it part of an all-consuming thing in my life. But like they found out. I was like, at the beginning of that show, all that static is on there. And there's like little Morse codes that are sent, and they're different for every show, and they give hints about what's going to happen in the show. Oh, it's crazy. All right, now that's good TV, man. That's good TV. All right. So the nucleus is only about 1 × 10 to the minus 13 centimeters in diameter. That's pretty small. Okay, pretty small. Now, obviously, different types of nuclei can be different sizes because the more protons and the more neutrons that are there, the bigger that nucleus becomes. So a uranium nucleus is very large compared to a hydrogen nucleus. Uranium has what, 90-some? Somebody give me their periodic table. Uranium has 92 protons. I didn't look at the mass to see how many neutrons, but you can imagine. You'd have to subtract the decimal number from that 92 minus from that decimal number you see there. Let's see. So 238 minus 92 is how many neutrons it would have. So you got all those neutrons, all those protons, and then with hydrogen, guess what you have? One proton. That's it. That's the nucleus of a hydrogen atom. Big difference between those two. Okay? The electrons move outside the nucleus, out here, with an average distance of about 1 times 10 to the 8th centimeters. Okay? So that sounds really small, but that's actually really big compared to the area that we're dealing with here. It's relative to where they are from the nucleus, they're a long way, even though everything is really, really close together. Okay? Oh, sorry. Therefore, the radius of the atom is about 100,000 times larger than the radius of the nucleus. Okay? So from here to here versus from here to the edge where the last electron would be traveling, you've got 100,000 times difference in size. So a ton of empty space in there. All right. As far as masses go, here's your subatomic particles. Protons, neutrons, electrons. Know that word too, subatomic particle. Here's the mass, the projected mass of a proton based upon a lot of experiments. 1.67 times 10 to the minus 24 grams. Look at a neutron. 1.67 times 10 to the minus 24 grams. So roughly a neutron and a proton are about the same in terms of mass. Look at the electron. 0.0009 times 10 to the minus 24. In other words, times 10 to the minus 24, 25, 26, 27, minus 28. Virtually massless. Okay? To the point where it's most of the time not even included in a lot of the calculations that you run into. Now, there's going to be another thing that we're going to use to make this easier, to come up with how much an atom weighs, how much mass an atom has. And what we're going to use is a unit called AMU. It stands for Atomic Mass Units. And it's easy because all we're going to do is say that since these two are the same, right, we're just going to say that's equal to 1. Makes it easy. We're going to say that this is equal to 1 AMU. So that means a proton weighs 1 AMU, and a neutron weighs 1 AMU. An electron weighs nothing in that scale. So that means it's easier. Now, if I ask you how much an atom weighs, you know there's 1 proton present, it would weigh 1 AMU. If it was a proton and a neutron, it would weigh 2 AMU. It's just we've made up this unit. Okay? Well, we didn't really make it up. It was a guy named Avogadro did a lot of calculations. Looked kind of like an alien. I don't know. Amadeus Avogadro. Nobody? He's going to have a very, very important number that we'll talk about here in a little bit. Protons, neutrons in the nucleus, electrons flying around in empty space outside that nucleus. Okay? Charges, you should know this. Charge of a proton is a positive 1. Charge of an electron is a negative 1. Neutrons have no charge. What do you know about charges? Like charges repel. Opposite charges attract each other. Why? That's beyond the scope of this class. You ever really ask yourself why? And you just believe it? We just go through our lives believing what people tell us. We don't explore things for ourselves. We take things that are not really ours and just sort of like the whole thing about the lady who chopped off the back third of her ham. That story. You guys heard that? Huh? Well, you got a lady, and she's teaching, her daughter is watching, and she grew up watching her mom how to prepare the ham in the oven. And she would always take the back of the ham, the back third of it, and chop it off. No one really knew why. The daughter grew up, and she did the same thing because that's what her mom did. And then, she had a daughter, and then finally that daughter asked, why do we do this? Why are you chopping off the back of the ham? Finally the lady says, I don't know. It's just what my mom always did. So she called her mom. They don't know. They started asking. Finally, they traced it back to the point was whoever did it first, the pan was too short to hold the entire ham. So they chopped it off. And then generations later, we're still chopping off the back of this ham. You can see where that applies to life in a very general sense. We do things because we've always done them. You keep doing things like you always done them, you're always going to get the same results, right? So keep that in mind as we go through. All right. Now we know about charge. You told me that opposites attract, likes repel. Okay, so that's what all this is. To be neutral, though, keep this in mind. There's two different ways for something to be charge neutral. Either it has no charge at all, there's no positive and there's no negative associated with it, or there's the same amount of positive as there is the same amount of negative and they cancel each other out. Either way, you've got a charge neutral situation. So keep that in mind. Okay, I talked about an AMU. If you really want to know the definition, I'm not just making it up. It's defined as 1/12 of the mass of a carbon atom containing 6 protons and 6 neutrons. You probably don't care. It doesn't really matter. Just know what an AMU is, that a proton is 1 AMU, a neutron is 1 AMU. Okay? So technically, if you do the math all the way out to more digits, you'll see that the proton AMU mass and the neutron is a little bit different. But it's so small that we just say they're both 1. Technically, the neutron is just a tad bit heavier than what a proton would be, but not to the point where it's going to make any difference in what we're doing. Okay? I'm going to start with this. I'm not going to get into the table, but I'll do this slide, okay? Because I want you to bring your table with you. That's good, so that I can start on that next time. Elements. Now we talked that when we said that what elements are, if you look on the table, what you look at the periodic table of elements, is all of the atoms that we know of that exist. And an element would be a sample of those atoms that can't be broken down into anything simpler, just those atoms themselves. Like a copper wire is nothing but copper, so it's elemental copper. Okay. So each element has a unique, each element that you see on the table, and thus we're talking about an atom of that element. Each one of those that you see has a unique number of protons in its nucleus. If you look at hydrogen, you will see, and I'll show you how to see this in a second in the next lecture. But if you look at hydrogen, it has 1 proton. If you look at helium, it has 2 protons. Lithium has 3 protons. Okay? Beryllium has 4 protons. Boron has 5 protons. Carbon has 6 protons. You can keep going all the way down the table. What you will see is that the only thing, the most important thing, how you can identify one element from another, by definition, is the number of protons in its nucleus. That's what makes 2 elements different from one another. 2 types of atoms different. How many protons does it have in its nucleus? That defines it. The second that changes, it's not the same element anymore. Okay? This is called the atomic number. So the number of protons in something is called its atomic number. If you have your periodic table, take a look at it. If you have one in your book, take a look at it. Whatever you need to look at, you will find, for example, look at hydrogen. You will find a number 1, usually at the top, either in the middle or the left-hand side of that square. Somewhere you will see a number 1 in the block with hydrogen. Not the decimal form, just a straight number 1. That is the atomic number for hydrogen. What that tells you is how many protons are in the nucleus of that atom. Look at sodium. What's the atomic number of sodium? 11. It's Na, it's sodium. Okay? No, K is potassium. Potassium has the atomic number for 19. What that tells you is that potassium has 19 protons, sodium has 11 protons. There's some other numbers on there. We'll talk about those next time. Okay? You should know this already. You will see that the organization of the table, look at it, you'll see a pattern. You will see that they are organized in terms of their atomic number. You start with 1 on the top left, and as you work across, just like you're writing, you go to the next line, you go to the next line. They continue to increase in nucleic size based upon their atomic number. Okay? Lastly, you should know that everything has a unique name and a symbol. What you need to know about this is you're either going to have a 1 or a 2-letter symbol. Potassium is K. Lead is what? PB. Anybody know why? What PB stands for? It is Greek, but what does PB stand for, the word they use? Anybody know? I'll show you why I'm saying this in a second. It's called plumbum. Think about what a plumber does. How they get their name. The earliest pipes were made of lead. The ancient Roman plumbing systems were made of lead. So plumbum is the word that was used for lead. Okay? Sodium is natrium. That's why it's Na. Okay? All right, wait, one more thing. Whenever you're writing these symbols, remember that if you have a two-letter symbol, one's capital, the second one is lowercase. You can't write two next to each other. Okay? For example, cobalt, it's big C, little o. If you write big C, big O, that's carbon and oxygen. Okay? Two different things.